Flashcard 31. The point -5, 12 is on the terminal side of theta. Find all 6 trig values. Any point, all 6 values. Compute r from the Pythagorean theorem. Then read every ratio from x equals -5, y equals 12, and r equals 13. To say it simply, first drop a point anywhere, find r with the distance formula, and then read all 6 ratios straight off x, y, and r. The formula is r equals square root of x squared plus y squared equals 13. Sine of theta equals y over r, cosine of theta equals x over r, and tangent of theta equals y over x. 3 problems to try. Number 1, 5, 12. R equals square root of 25 plus 144 by plugging in the values equals 13. So sine of theta equals 12 over 13, and cosine of theta equals 5 over 13. Number 2, -5, 12. R equals 13, so sine of theta equals 12 over 13, cosine of theta equals -5 over 13, and tangent of theta equals -12 over 5. Number 3, reciprocals follow. Cosecant of theta equals 13 over 12, secant of theta equals 13 over 5, and cotangent of theta equals 5 over 12. One tip to approach these kind of problems is to first plot the point, drop to the x-axis, compute r, and then read all 6 ratios from the picture. The background. The circular definitions work in every quadrant because x and y carry their own signs while r stays positive. Here, the point sits in quadrant 2, so cosine, tangent, and the reciprocals all come out negative, exactly as ASTC predicts. Part 32. Find the reference angles of 5 pi over 6 and 7 pi over 4. Reference angles in radians. Use the same reduction trick as degrees, just measured in pi. Locate the quadrant, then measure to the x-axis. To say it simply, it's the same reference angle idea as before, just measured in radians. Find the small gap to the x-axis. The formula for quadrant 2 is pi minus theta. For quadrant 3, it's theta minus pi, and for quadrant 4, it's 2 pi minus theta. 3 problems to try. Number 1, 5 pi over 6 in quadrant 2. By plugging in 5 pi over 6 for theta, our reference is pi minus 5 pi over 6, so our answer is pi over 6. Number 2, 4 pi over 3 in quadrant 3. Our reference equals 4 pi over 3 minus pi by using the formula for quadrant 3, so our answer is pi over 3. Number 3, 5 pi over 3 in quadrant 4. The reference is 2 pi minus 5 pi over 3, so the answer is pi over 3 again. One tip, for fraction sense, 5 pi over 6 sits just short of pi in quadrant 2, and 7 pi over 4 sits just short of 2 pi in quadrant 4. Background. Radian fluency means seeing 5 pi over 6 as slightly less than pi without converting to degrees. Students who translate everything back to degrees lose time on the AP-style questions where answers are expected in radians. Flashcard 33. Give exact values. Sine of 7 pi over 6, cosine of 5 pi over 4, and tangent of 5 pi over 3. Exact values are on the circle. First, find the reference angle for the size, then let the quadrant assign the sign. To say it simply, get the size from the reference angle, then let the quadrant decide the plus or minus sign. The formula is to find the reference angle first, then use ASTC for the sign. 3 problems to try. Number 1, sine of 7 pi over 6. The reference is pi over 6, and it's in quadrant 3, so it's negative. So the answer is -1/2. Number 2, cosine of 5 pi over 4. The reference is pi over 4, and it's in quadrant 3, so it's negative. So the answer is -√2 over 2. Number 3, tangent of 5 pi over 3. The reference is pi over 3, and it's in quadrant 4, so it's negative. So the answer is -√3. One tip, the 2-step habit. Size from the reference angle, and you get the sign from ASTC. Never guess both at once. Background. This skill is the backbone of everything in this set. Solving equations, evaluating identities, and checking models all lean on instant exact values anywhere on the circle, not just in the first quadrant. Flashcard 34. State the sector area formula and find A when r equals 6 and theta equals pi over 3. Sector area. A sector is a fraction of the whole circle, and the radian measure hands you that fraction directly. To say it simply, a pi slice's area is 1/2 times radius squared times the angle in radians, half of r squared theta. So the formula is area equals 1/2 r squared theta, and theta is in radians. 3 problems to try. Number 1, radius is 6, theta equals pi over 3. So by plugging in these values for the area formula, we get area equals 1/2 times 36 times pi over 3, which is equal to 6 pi. Number 2, radius equals 8, theta equals pi over 4. So the area formula is 1/2 times 64 times pi over 4, which gives us 8 pi. Number 3, radius equals 10 and theta equals 3 pi over 4. So by plugging the values, area equals 1/2 times 100 times 3 pi over 4. So the answer is 37.5 pi. One tip for memorization is that 1/2 r squared theta echoes 1/2 base times height, with the radius playing both roles. Background. The formula falls out of proportional reasoning. The sector is theta over 2 pi of the full circle, so its area is theta over 2 pi times pi r squared equals 1/2 r squared theta. Like arc length, it only works in radians, which is another argument for why radians are the natural unit. Flashcard 35. A wheel of radius 0.3 m spins at 120 rpm. Find w and the linear speed v. Angular and linear velocity. First, convert revolutions to radians for w, then multiply by the radius for the speed of a point on the rim. To say it simply, angular velocity is how fast you spin, angle per second, and linear velocity is how fast the edge moves. V equals rw. The formula is v velocity equals r times w, and w is in radians per second. 3 problems to try. Number 1. R equals 0.3, W equals 4 pi, so V equals RW, which is 0.3 times 4 pi. We can simplify this to 1.2 pi, so the answer is around 3.77 m per s. Number 2. 60 RPM. This means that W equals 60 times 2 pi divided by 60, so the answer is 2 pi rad over s. Number 3. R equals 0.5 and W equals 2 pi. So the formula is V equals 0.5 times 2 pi, which is around 3.14 m over s, since the answer is pi. One tip, unit check. RPM to rad over s means times 2 pi divided by 60, so a pi must appear in W. Background. Every point on the wheel shares the same W, but linear speed grows with radius. That is why the outside lane of a running track covers more ground per turn, and why gear ratios trade speed for torque.